Welcome to a lesson on the binormal vector. The goal of the video is to determine the binormal vector to a curve defined by a vector-valued function. Looking at this purple space curve here, this red vector would be the unit tangent vector, this blue vector here would be the unit normal vector, and this black vector here is the new vector, the binormal vector. And the binormal vector is orthogonal or perpendicular to both the unit tangent and the unit normal vector. And since it's orthogonal to both of these vectors, it makes sense that in order to determine the binormal vector-valued function, we must determine the unit tangent vector-valued function cross with the unit normal vector-valued function. Let's go and take a look at this in space to get a better feel for this. Again, here we have the space curve in purple, the unit tangent vector in red, unit normal vector in blue, and the binormal vector in black. Remember that the red tangent vector points in the direction of motion, and the unit normal vector points in the direction in which the curve turns as t increases. So as t increases, you can see how these three vectors are oriented, but at all times they are orthogonal to each other. You could almost think of this almost as a roller coaster, where the red vector tells the direction of the roller coaster, the blue vector tells in which direction the roller coaster is turning, and the black vector, the binormal vector, would be you on the roller coaster ride. Okay, so let's go ahead and see if we can determine a binormal vector. Here we want to determine the binormal vector at t equals pi over 2 to the given vector valued function. So we know we have to cross t of t and n of t, so we first have to determine these two vector valued functions. So let's go ahead and do that. So here's how we'll determine r of t. We'll find the derivative of this vector valued function. So we're going to have negative sine t, cosine t, and 1. And then we'll divide this by the magnitude. So if we square this, we'll have sine squared t plus cosine squared t plus 1. Well, sine squared t plus cosine squared t is going to give us 1. So it looks like we'll have the square root of 2 here. So our unit tangent vector valued function will be negative sine t over square root of 2 for the x component, cosine t over the square root of 2 for the y component, and 1 over the square root of 2 for the z component. Now let's go ahead and see if we can determine the unit normal vector valued function. So we have to find the derivative of this and then divide by the magnitude. So we're going to have negative cosine t divided by the square root of 2. Then we're going to have negative sine t divided by the square root of 2. And then the z component is going to be 0. When you divide this by the magnitude, so we're going to have the square root of, this will be cosine squared t over 2, plus, when we square this, we're going to have the sine squared t over 2, and this would be 0. Let's take a look at this radical a little more closely. We already have a common denominator, so we're going to have cosine squared t plus sine squared t all over 2. That's going to give us 1 over 2, or 1/2. This is going to end up being the square root of 1/2, which is the same as 1 over the square root of 2. Let's go and simplify this one more time. This is going to simplify nicely. Now instead of dividing by 1 over the square root of 2, remember we can multiply by the reciprocal, so we can change this to times square root 2 over 1. And we can see that these square roots are going to simplify nicely. So our unit normal vector valued function is going to be just negative cosine t for the x component, negative sine t for the y component, and 0 for the z component. So now to find the binormal vector valued function, we're going to have to cross this vector and this vector. And then we'll evaluate that at t equals pi over 2. Let's go ahead and do that on the next slide. So we'll go ahead and determine this by evaluating a 3 by 3 determinant. So the first row is ijk, the second row is from the components of the first vector, and the third row are the components from the second vector. Now we'll evaluate this 3 by 3 determinant by using the cofactor expansion method. So here we're going to eliminate row 1 and column 1. Here we'll eliminate row 1, column 2. And then lastly, we'll eliminate row 1, column 3. Let's go and evaluate these. Here we're going to have 0 minus negative sine t divided by the square root of 2. That's going to be positive sine t over the square root of 2. Here we're going to have 0 minus negative cosine t over square root of 2, which will be plus, but then we are subtracting, so it's still going to be negative cosine t divided by the square root of 2. Here we'll have sine squared t over square root of 2 minus a negative cosine squared t divided by the square root of 2. The numerator is going to be sine squared t plus cosine squared t. That's going to be 1. Our denominator will be the square root of 2. Let's go ahead and take this onto the next screen and evaluate this at pi over 2. Well, the sine of pi over 2 is going to be 1, so the x-component will be 1 over the square root of 2. But cosine of pi over 2 is 0, so the y-component will be 0. And then lastly, the z-component will be 1 over the square root of 2. This would be our unit binormal vector. Let's go and take a look at this. Here's our space curve in purple. Again, our unit tangent is in red, unit normal is in blue, and our unit binormal is in black. So when t is equal to pi over 2, which is approximately 1.57, the unit binormal vector that we found was something very close to this black vector here that we see. And again, notice all three of those are orthogonal to each other. Okay, that's going to do it for this video. I hope you found it helpful.